And if we have two vectors, say v has coordinates v1 to vn, and w has coordinates w1 to wn, then we can define the inner product of the vectors to be what is also called the dot product. And that is v1 w1 dot vn w. And this is an inner product. I'm sure you've seen it before, and I will not prove it here. One of the things you should always calculate is v inner product v, and if you do that, you see this is v1 squared plus v2 squared plus vn squared. We know this is always positive, sorry, and it is 0 if and only if v is 0. Moreover, the normal v, that is the square root of v inner product v, so this is the square root of this expression here. So this is an expression for the norm coming from the inner product. And I hope also that you recognize this. This is the so-called Euclidean norm. And this is really the norm we use to measure distances in R to V. Now, if we could do the same thing for v equals c to the n. More or less the same thing, but maybe emphasize it. So if we have two vectors v, w, and c to the n, then we define the inner product. You could again call it a dot product, but now it is v1, w1 complex conjugated plus v2, w2 complex conjugated, and so forth. So we do exactly the same thing as before, but we complex conjugate the second variable. Here we can then look at v inner product v, and that will then be v1 complex conjugated, v2 complex conjugated plus the dot, vn complex conjugated, using now results about the complex numbers. A complex number times its complex conjugate is the norm of the number squared. So we see this is a positive number. We also see the 0 only if all the vj's are 0, and that is the same thing as saying v is 0. So notice here why we take the complex conjugate of the second variable. We do that in order to make this positive. And we also finally see that the norm of v, that is the square root of v inner product v, and that is then root v1 squared, v2 active squared plus v in active. I will not verify the other parts of being an inner product. Then I will move on to function spaces. And the first example will be an exercise, but let me just briefly mention it nonetheless. Continuous function say from an interval a to b in complex numbers. Here we can define if I have two functions then we can define the inner product to be the interval from a to b f of x, g of x, complex conjugated dx. And the integral for that matter could be, it could be Riemann integral holiday. The only problem about using the effect here is that these are complex functions, and so far you have only seen the effect for real functions. Except that you actually have mentioned the Fourier transform. Lastly, that you've seen the exercise, and that is a complex function. So, and we will very soon see how to deal with complex functions as an explanation. But for now, we could even consider this as a Riemann integral. So at least for every two functions, you associate here a complex number. And if you consider f inner product f, then we see that this is integral from a to b, f of x, complex conjugate dx, and this is the same as integral from a to b, absolute value f of x squared dx. And we see this is positive. One can also see it is not quite as easy that this is 0 only if f is 0. The whole example here is an exercise. So you will do these details in the exercise sessions. Finally, the norm of f is f inner product f to the 1/2. So that is the square root of this expression. And this you have seen before. What is this? This is a 2 norm. This you have seen about it, 2 LP spaces. So the purpose of these exercises is also to see, give examples of inner product space and see also what is the associated norm. So this case, the associated norm is 2 norm. So now let us move more into measure theory. And so by the way, I should say this would be an exercise. And I will put it on the next sheet. Then we take ourselves a measure space. And let us also take something to begin by one. No, one more thing. I consider it 2, of course. So a 2 of associated with this measure space will be the set of functions that go from x to r, which are measurable. And such that they are square integrable. So this is a definition of 2. We know that Kepler says there's the famous Kepler inequality. And what Kepler says is that if I have two functions, then the product is in A1. So why is that true? Well, we use Kepler with P equal Q equal 2. And these are so-called dual exponents because 1 over P plus 1 over Q, that is 1 over 2 plus 1 over 2 is equal to 1. So hence, P equal Q equal 2 is an instance where we can use Kepler's inequality. So Kepler in particular says that the product of any 2 and 2 functions is 1. Okay. So maybe I can do over here. So after I want to define an inner product on L2, or one of the inner product rather, doesn't mind make it. So in other words, if I have U and V in L2 of U, then we can define like a wannabe inner product of u and v to be the integral u times v in u. And remember, this belongs to the 1. So therefore this makes sense, and this is a real number. One can check that it is linear in both variables, and it is symmetric, and I could rewrite this. And also, if I take u inner product u, what does that give me? That is the integral of u squared in u. And now these are real functions, so u squared is positive. So this is positive. The square of the real number is a positive number. So if I take u in the product u, I do get a positive number. And it's symmetric, and linearity in both variables is also okay. But it is not an inner product space. So with this assignment, this is not an inner product space. Not if we are very strict at least. Because the trouble is, what if u inner product u is 0? That happens if and only if the integral over u squared in u is 0. This is these same expressions. And now this is a positive function. So if I integrate a positive function and get 0, when does that happen? When can the integral of a positive function be 0? Yes, it's time.
When it's 0, almost everywhere.
That's right. So precisely, the u squared equals 0, u almost everywhere. And if the square is 0, then it's the same thing as u itself is 0, so we get this. In other words, u inner product u is 0 if and only if u is 0 almost everywhere. But that is not the same as saying u is identically 0. This is really what we wanted, and this is what we get. So it's not quite an inner product. So how do we fix that? And this is where the other LP spaces come into play. So the same problem as you have when you talk about LP spaces, the p-norm is not a norm, it is a semi-norm. And in many cases, you're quite happy with that. And in some cases, we may even also be happy with that we have an inner product which is like a semi-inner product. It's not completely bad, but sometimes you really want to fix this problem, and then here's how we do it. L2 of mu will be defined to be curly L2 of mu modulo an equivalence relation. And let me say that we define, let me just put it here. I say that u is equivalent to v if u is equal to v, mu almost everywhere. Let us use this. And then this is the same as the set of equivalence classes. My guess is that many of you have not really seen this before. It's kind of an abstraction. Let me try to make some drawing of what is happening. You can view L2 of mu. Think of L2 of mu as being a sausage, a big sausage. Then what you do is you slice it. And each slice is an equivalence class. So equivalence classes are precisely the set of functions u prime, curly L2 of u, such that u prime is equivalent to u, it's equal to u almost So each of these are equivalence classes, so this might be equivalence class containing U, maybe this is the equivalence class containing V. So here I will have U, I may also have a U prime here, and here I may have a V and also a V prime, and U prime are equivalent to V and V prime are equivalent. So anything in this slice here is equivalent to U. So this slice consists of all functions that are equal to U almost everywhere. And similarly, this slice here contains all functions which are equivalent to V, and so forth. So then what we do is we take a whole space and divide it into this kind of slices. Each slice is an equivalence class, and then this space here is the space of equivalence classes. So as a set, it is equal to the set of slices. Okay, and then as you have seen in chapter 12, probably quite briefly, is that the set of slices is actually a vector space. So LP, true I would call it, is a vector space. So the idea is that if I have two slices and I want to add them together, I do it the following way. So if, for example, I can even put it like here, so maybe U plus V as an element with true sits here, so it sits in a certain slice. Then I also have U prime plus V prime. And I can add those together. And as it turns out, that's here. So the fact we need is that if U is equivalent to V and U prime is equivalent to V prime, that implies that U plus U plus V is equivalent to U prime plus V prime. So hence, these two elements sit in the same slice. So that means that this is equal to, so I could also have calculated like this. These are equal, and then I would have gotten this, but they are equal. So the trouble would have arisen if this element was different from this, then I could not define the addition. But since we have this fact here, that means that addition is well defined. So you can take two slices and add them together, basically. Similarly for taking the product, alpha times U is alpha U. So you can think of that as maybe you have alpha U here, and here you have alpha U prime. So if U and U prime are equivalent, then these are also equivalent. This is the same size. Okay, so that is LP as true as a vector space. Then the next thing we do is we define an inner product. So the inner product of two slices is going to be this. And again, what we know is that suppose instead I had used different expressions. So the idea is, if you do any manipulation with a slice, if I want to manipulate this slice in a way, then what I do is I pick an element from the slice and then I manipulate with that. And then I hope that my manipulation does not depend on what representative I pick from the slice. So I could also have chosen different representatives, and had I done that, my inner product would have been U prime, V prime in U, but these are equal. And this is because if U is equal to U prime almost everywhere, V is equal to V prime almost everywhere, then U times V is equal to U prime times V prime almost everywhere, and then that implies that the interval uv is equal to the interval u prime v prime. So this is why we have this equality. So this interval is well defined. So this way, L2u with this inner product becomes an inner product space. And then let's now take the crucial addition. What happens if this is 0? Well, and I want to show this only happens if u is 0. But then in order to understand this, we have to name, there has to be a slice which is the 0 slice. So think of it, LP, L2 is a set of slices. And if I say a slice is 0, I should specify which one is it. So okay, so maybe this element here contains 0, so this now should be my 0 slice. And of course, you may also have all sorts of other elements, W and W prime. So then they will have the property that W is equal to 0 almost everywhere, and W prime is also equal to 0 almost everywhere. So the 0 slice consists of all functions which are equal to 0 almost everywhere. Okay, so now this happens if and only if I just look at my description, u squared, if u is 0, and we saw this happens if and only if u is 0, u almost everywhere. And this is, as I explained before, the same thing as the slice that u belongs to is the 0 slice. So that proves that this is an honest, in the figure the way he calls it, inner product. Now I want to say a few more words about this. So it's a little bit complicated somehow. We have curly L2. These are the set of honest functions. And the only problem about them is that you have this problem that the norm of a function could be 0 without the function itself being 0. But the functions are honest functions. Then you can make an honest norm space or vector space, but the elements are no longer honest functions. So what are they? What kind of objects are they? I'll just say just a couple of words about that, because sometimes you can say that, and this is really what linear equations do. If you have two functions which are equal almost everywhere, then you can identify them. Because they only differ on a small little part that you can neglect completely, so you identify them. And this is really what we do, but what kind of objects are they? So you can somehow say that elements in, say, L2 or mu are functions without function value. And let me illustrate this point. And then I will not philosophize much more about the p-spaces for now. I think nonetheless this is an important issue. Suppose we can take the example where our vector space is the most familiar one, namely R with duality algebra and the big picture. Okay, and suppose I have a function u in, say, L2 of lambda. The u is a function that goes from R to R. It's a class. Sorry. The u goes from R to R, and u itself belongs to curly L2 lambda. So then I can ask myself, okay, so certainly u of 0 is defined. Because u is a function, that is okay. But what about if I take the equivalent space of u, can I view this as a function? could I, for example, evaluate that at zero? So I'm asking myself, is this defined? So can I take an element of L2 of lambda, the non-parallel 2, and think of it as a function? So for example, can I take such a slice here and evaluate it at zero? Does that make sense? And the answer is no. You cannot do it because I can define a new function u prime, and that should be defined by u prime of x is u of 0 plus 1 if x is 0, and u of x if x is not. Then the set of points where u is different from u prime is precisely just signature 0. That's the only place where they're different, and this has measure 0. So the set where these 2 points are different has measure 0, hence they are equal almost everywhere. And that means that they belong to the same slice. So that means that if I want to, for example, define a slice of u at 0 as u of 0, then that should also be the same as u prime of 0, because these two slices are identical. It's the same slice. But this is u prime of 0, and u prime of 0 is u of 0 plus 1. And here you see a contradiction. It is not defined. So it's really a subtle point I'm trying to make, that this space is a very interesting space. We can kind of view it as functions, but they're functions without function values. So what you can do with these functions is you can integrate them. But you cannot say at a specific point what is the function value at that specific point. That you cannot say. So, okay. So I will not say more about this. It is a difficult point I'm trying to make here, and it takes really time to get used to it. Let me then move into the next issue we have.